Good morning, everyone. I'll start the webinar right now. So, the agenda for the webinar is as follows. First, there is a presentation. I'll walk through what Scilab is, what are the support models that is available, an introduction of Equalys and TechPassion, and some example programs on signal processing and image processing, and general features of Scilab for those of you who do not have an introduction to Scilab yet. Following this presentation, I will show a live demonstration of Scilab and show how to do some programming using Scilab. And following this, we'll take a few questions, and with that we will come to the close of the webinar. Let me get started right away. So, a little housekeeping topic. Everybody is placed on mute. So, if your question is how do you ask a question, you can go to the chat panel and type your questions. And as I mentioned already, towards the end of the webinar, I'll answer the questions before we close it. So, since you in the audience is placed on mute, I won't be able to hear if you have anything to say. But please feel free to type in the chat window for whatever may be the reason. Say you are not able to hear the voice properly, or if you have any questions as and when the presentation proceeds, put your questions there. I'll take it up towards the end. So today's topic is signal and image processing with Scilab. Suppose you are facing the challenge of having to pay upfront licensing fee and annual maintenance fee for your numerical computation software, and if your success requires state-of-the-art applications for your product or process development in various areas, from numerical computation to simulation to signal processing, image processing, control systems, and optimization. And you are facing problems with sharing licenses because it's too expensive to have your own license. And you are nervous about switching to open source because of perceived lack of industrial grade support. If you are facing any or all of these challenges, we have a solution, which is what I'm going to talk about today. Equalys has partnered with Scilab, a leading open source cross-platform numerical computation software, and TechPassion is the Indian partner of Equalys. It provides robust industrial-grade support for a complete open source solution. This solution has been downloaded almost 3 million times, and it is used extensively throughout the world in both industry and research. What is the Equalys solution? It brings the best of both worlds together. When you compare with perpetual licenses such as MATLAB, Scilab is a free open source application, and Equalys provides cost-effective industrial-grade support for training, migration, support, and custom development. When you compare with other open source solutions, Scilab is a full-time focused development team with a release schedule as compared to other random open source tools. And Equalys provides voice of the customer input into product roadmap and accelerates bug fixes. What's the background of Equalys? The company was founded in March 2009. It's headquartered in Silicon Valley, California, with global partners driving a vibrant online math community. And the site is www.equalys.com. Members can connect, share, and solve problems together. Exclusive partner of Scilab. Scilab, as I mentioned, is a leading open source platform for numerical computation. We provide a full range of Scilab support programs, from training, migration, email support, phone support, video tutorials, knowledge base, etc. We are an experienced team from industries such as Lockheed Martin, GM, Lucent, Google, BAE, Halliburton, and graduates of universities such as Stanford. I'm from TechPassion, and we are a company based in Chennai, founded 6 years ago, and a team consisting of alumni of Massachusetts Institute of Technology and IIT. And we have extensive experience in Scilab and Xcos. I'll talk about what Xcos is later in the presentation, but in a nutshell, it's alternative to Simulink from MATLAB for modeling dynamic systems, any kind of system modeling problems. You could use Xcos. We at TechPassion have domain experience in various industries, including automotive, aerospace, energy, among the key ones. Equalism today has a global network of partners. As you can see on this map, TechPassion is the partner of Equalus in India to support Scilab users in India. Equalus, you can think of it as a combination of Facebook and Red Hat. Facebook brings together a community of people who want to be in touch. So we at Equalus have built together a community of math people. So if you want to connect with other people who are interested in solving math problems or computation, Equalus is the place to be. You can register and it's free, and you can add information about yourself and join groups and forums. On the other side of it, a major portion of what we do is being the Red Hat for math. As you may know, if you have Linux and you need support, you would go to Red Hat. Similarly, if you are using Scilab for numerical computation, since it's open source software, the first question that would arise is, okay, to even get started, if I have any questions and I need some support, I want to migrate from my other numerical computation software that I'm using towards Scilab, who do you go to for support? It's Equalus. Equalus, like I said already, it's a math community. This gives a snapshot of our webpage. You can go there and register for free, and you can join a group, collaborate in various forums, and you can leverage Equalus solutions such as Scilab. You can download Scilab software from equalus.com site. There are Scilab support forums. There are also job portals. There are other problem solvers. You can provide answers. They could provide answers to you. Register for a lot of events which are continuously posted there, and many other benefits are there in being a part of the Equalus community. To download Scilab, you go to the Equalus site, you'll find a link to download Scilab. As you can see, it's available for Windows, Mac, and Linux. A brief overview of Scilab. It's a leading open source platform for numerical computation and provides a very powerful computing environment for engineering and scientific applications. It was created in 2003 by India, but the history of Scilab's development goes back to 91. India is a French National Institute for Research in Computer Science and Control, and there are many applications of Scilab, right from signal processing, control systems, numerical optimization, test and measurement, fluid dynamics, to embedded software. Supports a wide variety of industries, including automotive, aerospace, energy, defense, finance, chemistry, biology, medicine, and many other areas. We have a broad platform coverage, say Windows, Mac, Linux, and this gives a list of some of the large customers of Scilab or Equalus today. I want to give a few success stories from some of the lead users who have put Scilab for use in solving some of the advanced problems for industry. To start with Peugeot in France, they are an auto manufacturer and they make premium cars. So one of their problems that they wanted to solve was to reduce the engine noise in passenger compartments. So when you go to a showroom to pick a car, intuitively you would pick a car which is quieter. And the designers who are making these cars are continuously working on making the car quieter. And they don't do that just by trial and error. There's a lot of computation and simulation and testing that goes to it. So this particular case, Peugeot used Scilab to build an automation tool where they can compare their test data, that is measurements of noise using microphones, with their simulation models of how noise is present inside the car, and to correlate the data and optimize their design. Another success story is again from auto industry. Valeo is a component manufacturer based in France, and they are using Scilab to develop reliable modeling tools for studying the thermal loading of electronics hardware that goes into some of their automotive components. And they use Scilab for building this automation tool for rapid testing, and hence they have been able to improve the life cycle of their hardware by using Scilab in their product development. Vitas is a success story from the semiconductor industry. Vitas designs, develops, and markets high-performance, cost-competitive semiconductor solutions. And problem statement here, they had to create realistic data channel models and accurately simulate signal transmission through them. They used Scilab to build the simulation environment, base the simulations on TDR and TDT measurements of data channels. So, in the semiconductor industry, for example, they build automated test equipment where, say, you want to measure the voltage current characteristics of some transistors. Before going and actually building these machines, which are really expensive, you want to simulate in a computer the actual test. And developing these virtual data channels and modeling the circuitry and studying the behavior was what was done using Scilab. Today, Scilab is going through a lot of active development, and it's handled by an organization which is Scilab Consortium, and it consists of members from academia, industry, and public organizations, which are listed here, and it is growing every day. And recently, TechPassion also became a member of the Scilab Consortium, and we contribute to the development of Scilab software. If you look at the various components of Scilab, fundamental question is, why do you use a numerical computation software? Depending on what background you come from, you may have or you may not have introduction to programming at a low level. What I mean by that is, say I want to solve a problem. That is when I get into writing programs. First thing I need to know is learn a language, something like C++ or Java, with an understanding of what is the philosophy behind it, say object-oriented programming. Second thing, I need to get used to an integrated development environment, say something like Visual Studio or some other development platform. The third thing is I need to develop these algorithms, calibrate them, and make sure that they work. And also, the program has to be optimized. In this whole process, there is a learning curve involved, and you're losing time. When you go to a numerical computation software like Scilab, you have this all bundled as like one command, which is essentially a math function which embeds all of this, which means you are getting something done in a second instead of spending like 6 months on writing your own program for doing it. And most importantly, you are guaranteed about the accuracy of the results. And millions of people have already tested it. That's a huge advantage in using a numerical computation software such as Scilab. And it's a high-level programming language. And the other thing that we do with this computation software is visualization. So when I have data, I look at numbers versus I look at a graph. I get a lot more information visually. So it's absolutely important that you have visualization capabilities in the numerical computation software, and Scilab has it. Depending on what area of product development or research or teaching you are involved in, you may be using some sensors, or you may be doing some control. So you want to be able to connect to external devices. It could be something like a LAN port or wireless or USB or say some PCI interface, name it. You need to have some external interfaces, bring in data, analyze them, and send data back to the world. To do that, you can use Scilab. On top of all these functions that are available in Scilab has what are called advanced modules, which would be the equivalent of toolboxes in other software. And one of them is XCOS, which is used for simulation. And these are managed through Atoms, which is the automatic module management for Scilab. There are hundreds of such toolboxes that are available in Scilab. And how do you use these features in your application? It's being used in signal processing, control systems, numerical optimization, test and measurement, fluid dynamics, computational finance, embedded software, to name some of the key applications for Scilab. Coming to ease of use, it has a really simple user interface. You look at the software, you know what to do. And you can do algorithm development really quickly and deploy them and go to implementation. And if you have been a heavy user of MATLAB and you have a lot of programs from the past that you want to switch to Scilab too, the good news is there is a translator built in Scilab, so you can do a straightforward program conversion for your existing MATLAB program. Scilab has a lot of advanced modules. You can use Scilab for advanced signal processing, control system simulation, test and measurement, and embedded systems. Compare MATLAB and Scilab in terms of application signal processing. This lists some of the MATLAB toolboxes that are used in this area, such as signal processing, filter design, image processing toolbox. And then, if you look at the Scilab toolboxes, there is signal, image, and video processing, which is what I'm going to show you today when I get to the phase of showing some example problems and how we solve using Scilab. Beyond that, Scilab has equivalent toolboxes with respect to MATLAB for communications application. Say you want to write a program, convert it into a C program or generate executable which you want to distribute, you can do that using Scilab. There are excellent spreadsheet toolboxes and databases toolboxes, and there is Scilab which is used in aerospace applications. For numerical computation, there is symbolic math in MATLAB. In Scilab there is a SciMax toolbox, and if you are doing statistics, there are excellent toolboxes available in Scilab. And comparing with MATLAB, the Simulink in Scilab, there is Xcos. And if you are doing any kind of control systems modeling or design, you have CACSD, which stands for Computer Aided Control System Design Toolbox, which you can use for modeling continuous and discrete time systems. You can use it in linear systems, you can study nonlinear problems, you can use it in designing robust controls. You want to do system identification, you can do all of that using Computer Aided Control System Design Toolbox in Scilab. For optimization or quadratic programming, artificial neural networks, there are toolboxes in Scilab. There is also this parallel vector machine toolbox available in Scilab if you want to do like a parallel computing implementation. Net, Scilab has almost all the functions of MATLAB, and because of these toolboxes being available in Scilab, you have a flexibility which you normally won't have with MATLAB. So this, moving on to another big advantage of open source software such as Scilab and the way we are structured in Equalus is your voice of the customer is continuously heard, and that is built into our product roadmap and in the future release, right from simple fixes to introduction of new toolboxes to enhancements in Xcos and completely new ideas, implementation of features, OS support. We incorporate the voice of customer into the product roadmap and make sure that it's available in the future product releases. We provide the following support options. There is real-time support and online knowledge base. We help with efficient deployment and migration, and fast start application training, and special project consulting and development. Scilab online support portal, there is an online part where there is a lot of knowledge base available. There is documentation, video tutorials, you can ask an expert, and if you go to advanced documentation, there are thousands of pages of fully searchable HTML and PDF documentation of Scilab programs under categories under different applications that are available. And there are video tutorials available. And when it comes to interaction with our application team, there is chat, there is phone, there is email, and other desktop services. To contact Equalus support, there is a portal, there is a page on our site, and if you go there for India, right now it will be green and the live chat. So our registered support users or customers can contact us and get their questions answered live when they are using Scilab in their application. We have an education package. We have for Industry Pro and Pro Plus, and there is also Pro Plus Enterprise. This gives the various support options, whether it is Education Pro or Pro Plus, right from core application support to auto update notification to Xcos support, FTP download, real-time chat support. This lists various features that are available for different support categories. Now I want to go into a demonstration mode where I'll show some of the key features in Scilab and Atom. How do you install a new toolbox and user scenarios, say mathematical tools. You want to do graphing using Scilab 2D or 3D, say solving ordinary differential equations or differential algebraic equations, optimization, various areas, say signal or image processing, control systems, test and graphical user interface, XCOS simulation, MATLAB to Scilab translation. How do you do that using Scilab and XCOS? When you go to the Scilab console, you get something like this. There is a variable browser, there is a history browser, there is a command window, there is an editor window. And you want to access help, you go click on that and you get a help browser where there are various categories and under each of them the commands are listed and an explanation of the arguments and example program which shows how to use the command. Basic function to construct a random matrix consisting of 3 by 3, to build a random 3 by 3 matrix consisting of random numbers. How do you do that? That is shown in this slide, and it shows how to generate a column vector consisting of random numbers. How do you solve the system of linear equations where Ax is equal to B? Say you have a matrix A that is listed here, and I want to find the eigenvalues of the matrix. The command is spec of A. These are some basic functions in Scilab. Atoms, as I already mentioned, is the tool that you use in Scilab to install toolbox within Scilab. If time permits, I will show today how to do that to install a toolbox in Scilab. When you click on Atoms, it would list on the left a toolbox that you want to install, and on the right a description of it. It's as simple as just clicking on the install button and the toolbox will be installed on your machine. Typical user scenarios. I have some example programs here. Scilab has a huge assortment of graphic capabilities. You can do 2D and 3D plotting, special control systems, signal processing graphs. In control systems, you want to do Bode plot, Nyquist plot, or Nichols plot, whole zero plots, root locus. Those are built in Scilab. And there is also a MATLAB plotting emulation toolbox. Graphing examples, you can plot 2D graphs like this, you can do whole zero plots, plotting 3D graphs, and direction fields. Moving on to case studies, say advanced signal processing, you measure, filter, compress, continuous, real-world analog signal. It can include sound, image, sensor data, biodata, radio, and telecommunication signal. And various processes, you can do filtering, smoothing, pattern recognition, prediction, correction, or digitization. You can use Scilab. Signal processing toolbox. Scilab provides integrated toolboxes for signal processing such as time frequency toolbox, Scilab wavelet toolbox. There is linear system inversion, empirical mode decomposition, infinite impulse response filter, finite time impulse response filter. There is an image processing and design toolbox, image and video processing toolbox, say sound files, microwave data. So these are various categories of signals and different ways in which you will be processing them. There will be specialized algorithms for, say, when you go from general electrical signals to sound data to microwave. There are specific toolboxes that are available here. And these have happened over years of development and have been put to test already. And there's a toolbox for artificial neural networks modeling. And you can also do signal processing using XCOS. Many other related toolboxes. Let's take one example in signal processing. Say I have audio data. On the top you have a time series, audio signal as a function of time. The bottom you have the frequency content of the data. And you want to do some denoising in this audio file. Before that, let me take that clean data and add some noise to it. So I'm adding a Gaussian white noise with a signal to noise ratio of 25. That's added to this signal. This shows the noisy data on the top, and at the bottom it shows its frequency content. As you can see clearly, this is the original data. This is with noise. So the data is now corrupted with noise. Now I want to do some filtering on this using a finite impulse response filter. It's a linear discrete time system that forms its output as its weighted sum of a finite number of the most recent inputs, as you may know. That's the description of a finite impulse response filter. How do you construct it using Scilab? That is what is shown in this box. F type is a filter type, C trick shows the cutoff frequencies, and there is window type and the time domain filter coefficient. Say I want to do audio denoising by constructing a low pass filter with a cutoff frequency of 0.1 and there is a triangle window. Wavelets are mathematical functions used to localize both time and frequency by decomposing a time series into time, frequency, space simultaneously. So the reason I'm jumping to wavelets here is this is showing the filtering that was performed using a low pass filter, and it's no good because I started with this data, I made it noisy. When my filter works perfectly, I should get something as good as this output, but I'm not getting it. It's as bad as this. So I want to move to something better. So I'm using wavelets here for this application. And after I apply wavelets to denoise my signal with soft thresholding, I'm using this times unbiased risk threshold selection rule, and drawback is wavelet function of the 8th order. When I apply that wavelet filter, I get a really clean output. This is almost as good as what we started out with. The noise is completely gone. That's the power of wavelet, and there is a wavelet toolbox in Scilab that you could use for doing such filter operations. Another area is image processing. So we got this baboon picture, and I'm going to show some magic we do on this image using the image processing toolboxes in Scilab. What are some of the things that you want to do with images when you do computation? You want to read images, you want to display them, change from color to grayscale on the binary, and changing a grayscale image to its complement. You want to do some cropping, resizing, you want to add noise, filtering, edge detection, histogram, or you want to get some image compression done. You can do all of this and more using Scilab. Edge detection, this shows the construction for say single channel. So you got the picture of the baboon, and we do edge detection, and this shows under various parameter settings what is the output that we get. Say I want to get image histogram using the commands in Scilab. This shows the command for getting a histogram, and you want to get a cumulative histogram. This is the command. Now another area is image compression. So I have the baboon gray scale image, and this shows from the left to the right. Start with the original and set degrees for compression, and this shows the output from Scilab. Another application here that is shown in this slide is motion detection. So I've got a traffic scene, an image shot from the top of a building, and it shows the road traffic, two instances. So by comparing these two images, I want to be able to see what are the moving objects in the picture. Obviously there are some cars that are parked, there are cars that are moving, there is a pedestrian in the image, if you notice. And using the detect foreground function in Scilab image and video processing toolbox, we're able to take the two images, compare them, and say, okay, here is a car that is moving, here is a pedestrian that's moving, and that is done with this output. This shows whatever is shown in white. Those parts of the image are the moving objects, and they are shown in white. So successful motion detection is done using the toolbox in Scilab. Now say I have a video and I want to detect an object in a video. So here things are continuously changing. I want to locate the red car. So if I set the color using the cam shift function in the image and video processing toolbox, I can locate this car in the video. So those of you who are using Facebook would know, okay, I put a group photo there and I can tag the images. One of the things it does cleverly is face detection. Hey, you want to develop your own algorithms for doing it. This shows a group photo, and the function in Scilab helps me pick all the faces on that picture. So that's the face detection example we just saw. Now moving to object detection, say using this find best matches function in the image processing design toolbox, we can get all the triangles in this picture, which is filled with circles, small and large. There is a star, there are a bunch of triangles, and triangles are also tilted. So successfully this is able to detect all of them, and it is shown with these dotted lines with the red mark at the center. Another example, say we start with an input image of this chameleon, and say you want to study objects and want to separate them from the background. A camouflage application which is used in defense. Say there are soldiers who want to hide behind trees and so on. In nature, there are like things like chameleons which have the mechanism by which they can gel with the background. Say I have an image and I want to do some interesting image processing to detect the object and separate it from its background. So you want to develop some algorithms and test them. That's possible. This is one such example. Adding noise to an image. So we got a picture which shows a bunch of coins, and we want to show the salt, add the salt and pepper noise to this image. This shows there's a picture of a woman, and there is another picture, and we are adding the two images, and you want to find the difference between the two images. You can do that. Another area in signal processing, where you could either write scripts in Scilab, or you can use Xcos and do graphical programming. So Xcos is the tool in Scilab which is equivalent to Simulink in MATLAB or LabVIEW. It allows the user to build a wide assortment of models and perform simulations on those models. Very easy to learn and implement, and it has a good integration with the Scilab environment. So this shows an example where I'm starting with the original signal, and I add noise to it, and I can filter the data and get a denoised signal. So that's the end of my first part of the webinar. Now I want to show some demos using Scilab. So let me launch Scilab. So for those of you who are new to Scilab, let me show some simple examples. So you have this console window. Say I want to define something here. Space 0, 1, comma. So I defined this. One look at X. So this I've generated an array of 100 numbers from 0 to 1, equally divided. We want to do some simple addition. Times Y is going to give me the product of these two numbers plus Y. So this is how we can use the console window. Now I want to write some programs here. I go to Sci Notes. I'm going to define an array and plot parabola. So 0 to 5, my x-axis, and consisting of 200 entries. I want to find the length of this array. And for I equal to 1 to n, plot y of I is equal to 2 times x of I. So I define a parabola. I want to plot x and y. So that's a parabola of x. I'm plotting y as a function of x squared. So as I mentioned already, this is the console window, and this is the text editor where you can write a program. You can save it. I told you about atoms. So again, when you write a program and you execute, you can either execute with echo, which means it will list the entire lines of command so that you know, especially when it gives a error message, error in the program, if it starts and displays it, you know till what point the execution happened. or you can do an execution with no echo, in which case it will directly execute and give the output. So that's about how you write some simple programs. Now I want to show how to install toolboxes. When you select the module manager item, you will get a GUI like this. So on one side it will give you all the toolboxes and various commands, and on the left show you list of install modules. So in this case I have not installed anything. So let's say I want to install something for doing optimization. So when I select the optimization category, there's a whole lot of toolboxes available here. So I want to install the simplex optimization toolbox. It will give me some details and say what is the download size. It's only like 63 KB. And if I want some more information about it, I can go to these links. But all I want to do is install, so I click install. Obviously I'm on an internet connection. It's required for installation, but not for using the tool after that. It's as simple as that. Installation is done, then you restart Scilab to take changes into account. So I'm going to close this. I'm going to close Scilab. I'm going to reopen Scilab. So if you noticed carefully, earlier I didn't have this simplex listed here. So now I have the simplex toolbox. So if I go to the help, I would now start seeing the commands from simplex optimization toolbox that I could use in my work. So simplex optimization is listed all the way at the bottom. I can go here and some of the commands here, example programs are available. Null mean method, those of you who have used simplex optimization. Now, let me show a few other examples in signal processing area. Other thing, like I said, you can build GUIs using Scilab. So this is a DSP example where we have showed how to collect, how to display signals, how to do some filtering, how to set some parameters, and to do them all using a graphical user interface. So this is the program. So I built it with the GUI. I have a chirp signal. So this is the signal, and this is the Fourier transform of the signal. This is not meaningful for the chirp signal. For the signal where frequency is gradually increasing from a low frequency to high frequency. So what's more meaningful is a plot of frequency versus time, which is what you have here. So frequency is on y-axis, time is on x-axis, so gradually the frequency is increasing. Those of you who have not heard chirp signal, let me just play it. When it gets to the higher frequencies, it can be a little annoying, so I will start it and I will pause it real quick. I muted it, so it can, if it was annoying already, I'm sorry about that. So that's the chirp signal. So here, as you can see, this is a complete program. There is a user interface and some processing algorithm at the background, which is written also using Scilab, and visualization. So as you are seeing, this is a 3D plot projected in 2D, and other graphs, say time frequency domain. This is the chirp signal. If you want to think of it in time series, gradually it's a sine wave, and its frequency is gradually increasing, right? As you can see, it's getting between subsequent cycles, it's getting closer and closer. So I want to do some filtering on that, say finite impulse response filter. Say a low pass filter, say I want to set a cutoff frequency of 100 Hz. So this is the view, and now in the next view you'll get 4 plots. This is the time signal we started with, this is the FFT of the signal. I've done some filtering, so higher frequency should go away. This is what you observe here. So initially I have frequencies up to 4000 Hz or so. whereas after filtering, since I set a lower cutoff of 100, it is starting to roll off, which is reflected in the time series. The original chirp signal versus what I get after filtering are quite different. There are other options. You can have these drop-down menus, you can add radio buttons, you can have slider bars, and so on. So this shows the signal from a music file. So this is a typical audio from music data compared to what you saw with the chirp signal, which was a more defined signal which is used in system identification. So this is okay. So that's a small piece from a music file. And say we want to do some time frequency analysis on that. This is a time series, say Fourier transform of this data. You won't get a lot of meaningful information. This is the reason we use spectrogram or short-time Fourier transform. Okay. So this will give an idea of which are the ranges where, as the music progresses, what is the frequency content in the data, which bands do you have, or you can even analyze it in terms of which instrument is being used in which part of the music file. You want to do some filtering again, you can use infinite impulse response filter. Now all of this was built using Scilab. So we have used some functions from the signal image and video processing toolbox in Scilab. We have used the GUI builder toolbox in Scilab. And the Scilab is used for writing the scripts for various parts of the program, and a complete application has been developed. I'll show one more example from the image processing examples that I showed in my presentation today. So the phase detection program that we saw. These are the lines of program for it. So I'm reading the image, which is this one. So this is a group photo, which goes as the people.jpg. I'm reading this using this imRead command. Phases equals detect phases of IM. That's the function that I'm going to use. And I run this for loop to set up these rectangles and then display those on the image. Okay, I'm not on the right directory, so let me set the directory. So I have not activated the toolbox, so which is the reason we are getting all these errors. Okay, now I have activated the toolbox. Okay, so the program is running and this is the output. So initially we got an error because the current directory was not set right, and the next thing was though I had the toolbox installed, I didn't start the toolbox. So which you do by going here and starting, so then you have this. Then it would give an error because the command that I'm using for detect phases comes from the toolbox. So this is the output. I have shown this in the presentation. So I've done the live demonstration. That brings me to the end of my presentation. Let me go to the Q&A panel, take a few questions before the end of the webinar. Okay. Question 1. So are the toolboxes charged separately, or is it also free? Yeah, it's not really a technical question. The answer is the toolboxes are also available for download for free. There's not a separate charge. There's no separate charge for the toolbox. So what toolbox did you use for the image compression? As I mentioned already, there is signal, image, and video processing toolbox, and IPD toolbox. There is SIP toolbox. For this particular program that I showed in my presentation, I used the SIVP toolbox. Another question: do we have compilers similar to MCC in MATLAB? Yes, you can compile using Scilab also. Yeah, the question is correct. It is similar to MCC. It's not the exact same thing, but the answer is there is a compiler available in Scilab to take your Scilab program, convert them into executables or libraries which you want to distribute later. Is Windows-based Scilab also open source? Yes. As I mentioned already, Scilab is available for Windows, Mac, and Linux, and they're all open source. Specifically for version 5.3.2, yes. You're welcome. Okay, so there are a few more questions, and in the interest of time, we're already passed by 5 minutes. We would like to, I'll take one more question and we'll close the presentation. Please feel free to email us if you have any other questions. My email is Dhanush, DHANUSH@techpassiontech.com. For accessing ports, USB, serial port, etc. in Scilab, which toolbox to use, there are multiple options. There is a hot toolbox, and there are some drivers called comedy drivers. You can use them for accessing the ports. Can we have a copy of this presentation? Yes. We will make the recording available for you, and we can also make the presentation available. Okay, so that brings us to the end of the presentation. Thank you for participating in the webinar, and have a good day.